So the assessments, the answer certainly to, well, you're going to have to go beyond the material in the lectures to answer the assessment questions, because otherwise you wouldn't be doing any thinking. So in some sense, you will be extrapolating to do the assessment. And of course, you can look at external materials to help learn that stuff. But it's not, certainly the way I'm doing my lectures, I don't know if Ferenc and Nick want to comment. I'm not assuming that you've looked at the other material. I'm trying to put everything, all the pointers you need to answer the questions in my own material. I can see Nick nodding. Is that the same with yourself, Ferenc? Yeah. Any updates on the format of the assessment? So it's going to be sort of a series of short questions and shortish questions from the given lectures. And as I say, 30% from the first 3 weeks. And then the last 2 weeks is 70%. So you might think that's a bit odd, but of course you'll have had more time to digest the first 3 weeks. And there's sort of quite a lot of material in the last 2 weeks in terms of giving you capabilities to do stuff. I think we're not doing assessment in pairs. We were thinking about that, but we've got the numbers low enough. We sort of discussed it. And the numbers are low enough that we're happy to sort of mark them individually. That was kind of because we were a bit worried about numbers for the first time. Any other questions? It's possible to allow participants. Yes. Yes, it is. Yes. I just haven't set that up. Brilliant. Okay. Right. So if there's no other questions, I'm going to share screen. Sam, yes, there will be some maths questions. So the question is, will there be some mathematical questions or will there be coding tasks? And yes, there will be some maths questions. Okay, can we see that? Yep, is that good? Okay, as I said, so today, generalization and neural networks. And I want to start by looking at, as I say, a simpler system, quadratic loss and a linear system. But I'll start with this formula really, because this is in some sense is the gold standard for generalization. So in machine learning, you define some loss function, and your typical aim is to find a set of parameters in that loss function, which here we've denoted with W. That means that the predictions you make through a prediction function, where you've got an input for X and some response variable Y, are matching those that you see in the real world. And here I'm representing that formula with what's known as the expected loss, or sometimes called the risk, which is why I've denoted it with R of W. So this is a formula that we would like to be able to deal with. But here P is a distribution we don't have access to. So this is something that's happening in the real world to give us our inputs and our targets. So somehow the real world's generating things, and we represent that by a probability distribution P. Now, what we would like to do is minimize the loss over all possible things the world is going to produce, well, things of interest, the Y and X. But in practice, we don't have access to that distribution, so we can't do that. So the core idea in a lot of statistics and machine learning is known as, well, in machine learning, it's sometimes known as empirical risk minimization. So the idea is the following. You can do a sample-based approximation. So that's the top thing here, to the thing you're interested in. So any expectation of some function f of z under some distribution p of z can be approximated by samples from p of z. So if zi is a set of samples from p of z, so there's s samples, then this approximation is roughly right. So the typical approach for many machine learning algorithms is to look at what's called the empirical risk and minimize the empirical risk. So that's now represented by our loss function, whatever form it was. And now we've got a bunch of samples from P of X, sort of funny shaped Romanish P. And each of those samples is a pair of inputs and targets xi and yi. And the relationship between them is given through our prediction function by some parameters w, which in the neural network would be the neural network weights. And the aim is to minimize this loss. But this is a sample-based approximation. So the problem is when we're minimizing this, we're not necessarily always minimizing that. And a lot of the art of generalization is trying to deal with that gap. So the fact that when you're minimizing the empirical risk, you're not actually managing the risk that you're interested in. And there's different approaches to dealing with that. Statistical learning theory is all about gaps between the empirical risk and the true risk. Bayesians take different approaches, et cetera, et cetera. But to sort of set the context for how we should think about some of the interesting stuff that's going on in neural networks, I'm going to look at a very simple system. And we're going to look at the quadratic loss. So the quadratic loss is normally used for regression, although some people do use it for classification. And the idea is your prediction function, f of x, comma w. So this would be like a neural network output. But in a moment, I'm going to make it even simpler than that. The difference between your response variable, y, the covariates, so the covariates are sort of the input to the neural network. The idea is, this is a statistics term, the idea is that they vary with the response variable, the variable of interest. So the risk is just the sum of the squared differences. So I mean, you'll have seen that as far back as high school, I suspect, in a lot of countries. It's called least squares. So this is a sort of, the idea in this case is that your loss is quadratic. Somehow you're paying a penalty for gaps between your predictions and the truth, which is going up with the square of the difference. And with the sample-based approximation, we've dropped the 1 over n because it's just a scalar. We look to minimize this. Okay, but what I'm actually going to look at in this session is something simpler, which is a linear model. And there's examples of the linear model in the notes. So the linear model is good because it allows us to play with a lot of the ideas behind generalization with fairly straightforward linear algebra to do things that currently aren't possible when we're thinking about neural networks. And it also gives you a sense of the type of issues that come up. So this is the object I'm interested in. And the idea is I'm trying to minimize this risk with respect to these parameters. Okay, so in the notes, you'll see I do everything in terms of design matrices. Apologies for this. That should be a phi, a bold phi. I was trying to fix that and I couldn't. So I've just left it in. That should be a bold phi. So it's a bold phi because in general, X in a linear model might not be a direct observation of the feature. It could be a nonlinear variant of the feature. And we'll come back to that in a minute when we look at a polynomial basis. But that starts getting us a little bit like a neural network. So in general, what we're trying to do here is not necessarily X here, but a vector phi. So in order to do the maths we do in the notes, what you'll see is I make use of this trick a lot. So in order to represent things of interest, so this vector f is the observation of the prediction function f at all values of xi. So it's a shorthand. F subscript I is the evaluation of this for a given set of parameters. So I'm dropping a load of the notation there. And then I'm saying that that gives me a vector, which I'm stacking in columns. So these are each scalars, the evaluation of the prediction function at each point. And now this is my loss. Is just can be written in this way. And the reason I'm doing that is because I kind of really like to do my calculus in matrix form because it makes it easier. So you'll see it going through that stage by stage in the notes. But if I make that definition and then y is similarly defined as the response variables, the vector of all response variables. So there's sort of n of these and there's n of those. So then I can do y minus f. That would be called the residual because it's the difference between the response and the target. and I can do an inner product of those. So this is a vector in a product. I'm using matrix notation. So that's like a column vector, but it's transposed. So it's a row vector. That's a column vector. These are being multiplied together. And that is just another way of writing this. Okay. So I was just going through that, so you're not sort of surprised at what comes up. Now, I did have that vector phi as well. And unfortunately now I have got the matrix phi. The other thing I can then do, given my definition, is write f in this matrix form. So you'll see it's gone through more slowly in the notes, but basically I can also now have this very nice linear algebraic form for the output of my model. So in this case, it's a design matrix. And a design matrix is a matrix of features. So each row of this design matrix, as you sort of like, what you should imagine is n rows and then say k columns with this k features. And each row of this design matrix is a vector phi. And because of the way I'm defining things, I can now write my prediction function f as phi times w. Now, this is a key object. So make sure when you go through the notes, you spend a bit of attention on that. The reason it's defined in that way is because statisticians have defined the design matrix to have the features in the rows. Sometimes you might see people, particularly in engineering, who use it in the transpose form. I think quite sadly in the Gaussian process book, they use it in the transpose form. But I would avoid that because you'll confuse statisticians and they define it first. So this is basically our model where phi is containing rows containing x and f is containing the output. I hope that this is review, that you should have seen linear models before, but I'm aware you'll all have done different courses. So you may have seen it in different notation. There's more sort of review in the notes if you're not familiar with it. Now, what we want to do is we want to minimize that objective with respect to the parameters w. And there's a trick which is really, really nice. I don't know how much multivariate calculus you remember or whether you've looked at it before, but once I've got my system in this form, I can substitute phi w in for f, and I can multiply out these brackets. And now I have my loss in a sort of matrix form. And the way that it appears is what we call a quadratic form. So like if I multiply this out, what I get is y transpose y minus f transpose y, this is all in the notes, minus y transpose f, which is the same as f transpose y because it's a scalar. So y transpose y minus 2f transpose y minus plus f transpose f. If I substitute in phi w, what I get is a bunch of quadratic forms. So I get a bunch of terms like this, well, two terms like this, one which is the form d where a is equal to y, and one is which is the form where capital A is equal to phi transpose phi. So to minimize that, I need to take gradients. And the really nice thing is if you sort of know a bit about multivariate calculus, you can just do these. And these are the only two gradients I'm basically going to use for multivariate calculus. This is a scalar, the inner product of A and W, and this is a vector, W, right? So this is the differential of a scalar by a vector. And there's a few different ways people define multivariate calculus, but I use the way where the scalar by a vector should be a vector, right? And in this case, that's what we've got. So A is a vector. Similarly, if A is symmetric, then, well, sorry, if we've got this, this quadratic form, so we call this a quadratic form in linear algebra because W is appearing twice. So in a sort of standard scalar case, if we took the special case of W and A where we reduced them to W to a one-dimensional vector, A would be a 1-by-1 matrix, and this would be just W, A, W. So that would be W squared A. But the quadratic form in matrix algebra looks like this, right? So you end up with a vector transpose times a matrix times a vector. There's a lot of sort of little bits of vector review in the notes for those who don't remember it well. I should make sure I'm seeing, so I haven't pulled the chat up in case, do interrupt me if there's something not clear. Okay, so I'm hoping this is all review, but I'm familiar with the fact that you might not have seen it in a while. Now, that result is that we get a linear term. So if we take the gradient of that with respect to W, we get A plus A transpose. But if A is symmetric, we get something that looks very much like the result for a quadratic. If we take the derivative of AW squared, if it's all scalar, then we will get 2AW, and it looks very similar. Okay, so these are the two multivariate derivative rules you need. And if you do that, and sorry, I'm flipping between X and phi here, you can get a solution for W. Again, all in the notes. So what you do is you take the derivative of the loss with respect to W, and you recover a formula for a quadratic form. Okay. So in the matrix notation I'm using, this is what this looks like. So I defined phi. So X is all those features on the inputs. And as I said, phi is going to become a really important object, so that phi transpose phi is a matrix. So each of these is a vector. So if you look at what's going on here, this is the sum of the features that are going into that design matrix. And they're outer products. So this becomes a k by k matrix, but it's summed across n times. Now in matrix form, if my design matrix definition was that each of these x's are in rows along phi, and when I multiply these two together, I get a k by k matrix, which is in the form of a sort of outer products, just like is shown here. The other term that pops up is this term. So looking here, these are the two terms in my solution for W when I set the gradient of W to 0. And those are the two terms I'm rewriting here. So the reason I'm going to all that effort is to substitute this equation here. This one here, again, it's in the notes. I haven't talked about it here. It's less interesting for what we're talking about here. It's if you choose to view it as a Gaussian noise. But this is the term of interest here, right? So what I can do is I can write down an update for W that is of the form of inverse of this matrix times phi transpose Y. And that's the standard multivariate linear regression update being done through in a matrix form. Now, why have I spent the time doing that? Well, because this object here, which is emerging, this matrix of basis functions, turns out to be really important. Sorry. I'm going to switch to, let me just fix that, because that is bad. Sorry, the Hessian there is a key object. I've accidentally put the gradient of that term in. So let me just fix that. So what I want to look at now, or the reason I've sort of focused on this object here, is because a really important object that comes up a lot in terms of generalization is the Hessian of this loss function. So far we've been looking at the gradient of the loss function and solving this linear system in order to get a position where we've got the optimal value for W. We've minimized the loss with respect to W. Now let's just see if that's worked. Okay, that's better. So this is the Hessian. So if I take the second derivative of the loss function with respect to W, I was left with this, when I was solving this form here, I had that on the other side because I had this linear term, and that again is gone through in detail in the notes. I end up with this object here, which is simply the Hessian. Now, why am I talking about the Hessian? Because the Hessian matrix is the curvature matrix. So again, this may be a review for you, but when you're doing an optimization in a sort of univariate case, and you're trying to decide whether something's a minimum or a maximum, I don't know if you remember, but you'll then often take the curvature, you'll take the second derivative. And if the curvature is positive, that tells you that you've discovered a minimum. If the curvature is negative, that tells you that you've discovered a maximum. Now, the object we've been dealing with is just a multivariate quadratic form. So if you think about the curvature of a normal quadratic, you'll find if you take the second derivative of that, it's just a constant. It's a constant number. And very similarly, in this quadratic loss function, if we take the sort of second vector derivative of it, we get this matrix form here, which is based on this design matrix. Now, this design matrix, this form has a number of properties, including its positive definite. So what do we mean by positive definite? A matrix A is positive definite if for any vector u, where here I've constrained the length of u to be 1, but actually the length of u just has to be positive. This little quadratic form, u transpose A u, is greater than 0 for all u. So this matrix, it's strictly positive semi-definite, but in the cases that we're interested in the beginning, is positive definite. So what this means is that the curvature of this surface is positive definite. It's also not dependent on W. So when you, this allows us to say that this objective is a convex surface, right? Because what it's saying is wherever we are in this surface, regardless of W, we have the curvature to be a positive definite matrix. And that's the definition of a convex surface. It means it's constantly curving up. And that tells us that there's a unique minimum, that it is a minimum, because a positive definite in the multivariate case is the same as positive in the univariate case. And the minimum is unique. But this object is also telling us the shape of the minimum. So if we look at the eigendecomposition of the Hessian, so remembering the eigendecomposition in matrix form, if I have a matrix A and I multiply it by U, where I've decided U is an eigenvector this time, so U is the same as defined here. If I can solve this equation for U, where lambda is a scalar, then U is defined to be an eigenvector of A. Now that's, the way I like to think about that is that U is just a direction in this very, very high dimensional space. But it's a particular direction. It's one where if I take the eigendecomposition of phi transpose phi, so if I look at the eigendecomposition for phi transpose phi, what I'm finding is the principal directions of curvature in this Hessian space. So this phi transpose phi is a very high, well, potentially, it's a high dimensional object. If we're doing linear regression, it's in one dimension, it's just two-dimensional. But in general, this phi transpose phi can be a sort of, it's a k-dimensional object. And what happens in neural networks is k gets pretty large. So you end up with this phi transpose phi as a high dimensional object, and you're looking at curvatures. You can look at the curvature of that through the eigendecomposition. Okay, so why am I going into this linear model? Well, because the type of analysis that you do as you go through the notes in that linear model is relatively easy, and it's not easy in, say, a deep neural network. So comparing what we're talking about from the linear system to a deep neural network, what we have in a deep neural system is we've got a number of inputs. We do have a set of basis functions, but this set of basis functions is a nonlinear set of basis functions. So at each output here, in neural network parlance, this is called an activation function. So each of these in a neural network would typically be a rectified linear unit, but we can just think about this as a general nonlinear function. And at each layer, what we have is some non-linearization of the previous layer feeding into the other. This is a fully connected neural network. Obviously, if you start doing things like convolutional neural networks, you don't see the same structure as we're seeing here. So at the top layer, it is a linear model, but the input is not x directly, it's x going through some set of basis functions. But in general, that turns out to be, certainly in the terms of these parameters, what we would call a linear model as well. And the reason that this linear model that I'm going to review how that happens by looking at polynomial basis set in a moment. And if you look at a lot of the literature on terms of generalization in neural networks, that's the form of model they tend to focus on because it's analytically much easier to deal with. Okay, so mathematically, what we're saying is the neural network form has this series of basis functions here, but I can write my prediction function now in this way. So this is what we mean by deep. We mean compositional. A series of nonlinearities, so each of these is a vector valued function giving us a nonlinearity. A series of nonlinearities is composed together in order to form an output function. So all those fancy diagrams mathematically are just composition. Now, from a mathematical perspective, you say, well, why is that interesting? Well, because these functions are relatively simple, but by composing each of these nonlinearities together, in the neural network case, ReLUs, you get a relatively complex function at the output. And indeed, as we're going to see in later lectures, if you structure these inner functions here, you can start to impose things like the convolutional structure. You can bring in invariances that you're interested in. Okay, so in the notes, we've got a simple linear regression, which is just going to be multivariate linear regression looking at some health sites in Nigeria. So the data is downloaded from the web. And all you're going to do is just to review the linear regression, a multivariate linear regression. You just have a play with that. And what you'll see is I've got you to regress the number of, as covariates, we've got for each of these sites, the number of nurses and the number of midwives. And for your response variable, you've got the number of doctors. But I've also asked you to include latitude and longitude because we have them as covariates, and to see what happens there, what type of result you get, what the good prediction is, like are there more doctors in the north or the south, or are the doctors really just dependent on the location, the number of nurses, related to the number of nurses and number of midwives. So that'll be a linear regression review. Okay. But the interesting feature is if we start going to a basis function model. So my perspective on neural networks is very much that they are just basis function models, but they're adaptive basis function models. So they're a bit more complex. So what I want to just review is what the nature of a basis function model is and how we get a nonlinear prediction in what we would call a linear model. Because as I say, many of the results around generalization and our understanding of neural networks and overparameterization are coming in these linear model forms. So the idea behind a basis function, and in this case, we're going to consider the one-dimensional case. So we have a set of bases where each basis function, and in this case, I've denoted them phi j of x, and these are the things that make up our design matrix, is given by a function. And we're going to look at the polynomial basis because it does a nice job of overfitting, and I want to emphasize overfitting. In practice, you should rarely be using a polynomial basis for data fitting in the real world. So this polynomial basis is made up of all the sort of a combination of, say, an offset, a linear function, and if we just use these two bases, then we just have the linear model we've just been talking about. But we can then augment by a quadratic term, and we can augment by a cubic. Hopefully this is review. So the idea here is that we can take a series of functions, and here's a quartic as well, and make a new function out of them by adding them together. So here's a set of function that is derived from a polynomial basis. So I've sampled some parameters W, which I'm showing here in the colors associated with the associated basis function. So, and then you can see the white line is the result of adding together these different bases. So we have W0, which is the offset. So that's being multiplied by 1. So there's nothing appearing here. And we have W1, which is the linear term, which is 0.3. So what we should see when we look at the white line, it does look like there's a gentle slope going upwards, which is associated with this gradient 0.3, but it's offset down from 0 because of this weighting on the offset. Now that's the linear term. If we add in the quadratic term, which is here, W2, that's giving us a slightly negative curvature. Yeah. So if we were to take the second derivative of this, it wouldn't just be W2 because it would have terms that are dependent on x4 and x3, because this isn't a pure quadratic. But if it were a pure quadratic, we would just recover W2 as the curvature. And again, W4, which is also contributing to the curvature a lot, is 0.14. So that's how we get the function out of there. And I can sample different functions through different weightings. So by changing the weightings, you can see W is moving. And that's the basic idea behind a basis function model, that I can create nonlinear functions, but we still call this a linear model. Why do we call this a linear model? Because it's linear in the parameters. So if you look wherever W appears, there's no nonlinearity around W. Now, neural networks in general are nonlinear models, but this is the type of model that a statistician might play with because it keeps linearity and it keeps interpretability around the parameters. So we can get nonlinear predictions with a linear model. And we're going to look at a sort of example of fitting that. Again, you got the code in the notes for how to fit, and you should go through that. Where we're looking at a favorite data set of mine, which is marathon pace times for all the Olympics. I think not including the most recent one, but certainly up to London. I think it doesn't, maybe that includes 2016. So this is the pace of different marathons. I like this data because it's got some shape to it. It's also got this outlier. So this outlier was in 1904 when the marathon was in St. Louis, and people involved cars for the first time, which kicked up dust, and everyone sucked on the dust and they got lost. And so actually this is a feasible marathon time for a normal human. All these are very fast marathons, much faster than I could imagine running it. Alan Turing, by the way, is pretty fast at the marathon. He would be, I think, up here somewhere in terms of pace. But over time, the marathon speed's gone down. And we can fit a linear model through looking at the, using the formula that we've just been through, that W update, to this data. And if we do a linear regression, there it is. It gives us this offset, and it gives us a gradient, and it fits the data in some way. But we don't like that fit, perhaps, because we might think that that fit isn't really reflecting the fact that the marathons don't seem to be continually speeding up. And that's where we can use polynomial bases. So this is a cubic fit. So by adding a quadratic and a cubic term, we can fit again, and we get something that looks somewhat nicer. So it's going through these points here. But when it comes to generalization, we're interested in how well these are going to predict other data. And we could ask, well, why stop at cubic? Why wouldn't I go to a 9th degree polynomial? So yes, definitely the 9th degree polynomial is doing something funny at the sides. And if you were trying to use this model for extrapolation, you might be quite worried about how that behaves. So it's very characteristic of a polynomial. What I've actually done, and you'll see it in the code, is I've scaled down this region to be between -1 and 1. And if you ever are fitting polynomials, you should always use a scaling like that, because as soon as you get out of the -1 to 1 region, you get this horrible behavior with polynomials. So the polynomials sort of flying up and down in these spaces, right? Oh, so why stop there though? We could go for a 26th degree polynomial fit. So why am I showing you this one? Well, this one's interpolating the data exactly, because I'm using a polynomial that is the same order as the number of data points. And that means that we now have sufficient modeling capability that Hessian matrix is now full rank and the same dimensionality of the data set. So this gives us a particular system. When we're in these cases here, what we're actually fitting is called an underdetermined system. So to fit this straight line, we have two unknowns, M and C, or in our case, W0 and W1, and we've got 26 observations. So if you set that up as a system of simultaneous equations, you've got 26 simultaneous equations with two unknowns. So sorry, did I say underdetermined? So it's an overdetermined system. It's an overdetermined system because there's far more observations than there are parameters in the system. So it's an overdetermined system. Now that is solved by minimizing the least squares. So this whole all this effort we do here in terms of specifying a loss function, all the way back, so I shouldn't go back far back. All the effort we do in terms of specifying this loss function here is to deal with the fact that we will not. So we're minimizing the squares because we don't expect to be able to fit y directly, because the number of unknowns in this system is far fewer than the number of data. But then as we increase the number of parameters, we increase the number of basis functions we're using, we're starting to see that we can more closely interpolate the data. So with the 9-degree system, it's still an overdetermined system because there's now, in this case, the cubic fit, there's 4 parameters, 26 data. In the 9th degree polynomial, there's 10 parameters. It's 9 degrees of polynomial, but remember there's a basis function at 0, the constant, so that's 10 parameters. And then with the 26th degree polynomial, it's 27 parameters. So actually there must be 27 points because that's the highest I can go to. And what we now get is the same number of parameters as data points. And this system is now well determined. It's not under or over determined. It's solved exactly. But problematically, it's not what we would describe as a great fit. Now, I've used polynomials because they really exaggerate this effect. Like if I were to use other basis functions like ReLUs or RBFs, you wouldn't necessarily see these horrors to such a great extent. But that's kind of why I've used polynomials in this case, because when they fail in this very dramatic way. So we're interpolating exactly the points. We're going directly through the points, but our regions between, when we interpolate, are not always good. Like particularly here, they're flying up and down. Okay, so what I want to introduce you to is an idea that comes from statistics, which allows us to quantify that effect, and it's called the bootstrap. So in general, what we assume is that we're getting our data set from this true probability distribution that we don't have access to, the one I remembered at the beginning that is associated with the risk that we're interested in. But in practice, we're just given one sample from that, y and x. Now, if we wanted to understand the variation in our fits, what we could try and do is get multiple different samples from that and fit multiple times. But our fit is going to be better if we use more data. So every time we do get a different sample from that P of x, we're kind of wasting it if we're using it to check the variation. So the bootstrap is a sort of approximate way of checking that variation where we sample from the data set we're given. So this would apply to x and y here, but I'm just sort of showing it for illustration purposes. And we subsample our data with replacement. So all this is trying to show you here is using the Python command random choice. So this is just giving me sampling with replacement integers from 1 to n. I'm sampling from the integers 1 to n with replacement, and that's really important so I can have the same integer twice. And the bootstrap sample is the same length as the original sample x, so that's being set there, sampling with replacement, right, from the integers 1 to n, and then just return a copy of that. Now some of the rows are going to be duplicated. And the thing that you'll see in the notes, and I'm going to show the results of now, is doing bootstrap fits. So why is that interesting to do? It's an approximate way of getting something that looks a little bit like the thing we really want. So what we really want is a joint sort of sample. This is our matrix of covariates. This is our vector of responses being sampled from this distribution here. But in practice, we can't do that. So we resample. It's a resampling trick. We're resampling our data x. And when we resample our data x, we can fit with the bootstrap instead of fitting the original data. Now, these are just the same models as before, but here I'm showing bootstrap sample fits, right? So what you start seeing is as I vary the bootstrap sample, I get different linear regressions. Now, there's they're fairly consistent. And of course, if I were to just be, so here, this is basically a 2-parameter system. I could look at the 1-parameter system, which would just be predicting with the mean of the pace time. Now, in this 2-parameter system, what I'm seeing is I see slight variation in the parameters I'm learning, and you can examine what that variation is in the Colab notebook as you look at it. But I'm seeing some slight variation in the gradient, the offset. So this little bit of error is what we consider is variance in the quality of the fit. So if we look at different data sets, so in this case, they're resampled from this data set because we don't have we can't rerun all the Olympics from the past. This Bootstrap approximation gives me an estimate of how these fits would vary with those different data sets, right? It's a really, really powerful method, actually. It's one of the most important methods in statistics because you can sort of do this with any statistical analysis you're doing, right? And you can analyze this type of variance. The problem is, of course, if you're doing a very large model, like a neural network, it involves multiple fits of the model. So to do this one, I've done 10 fits, right? So you have to fit the model 10 times. But for small data sets, Bootstrap is a really powerful method of estimating the uncertainty in your fit. Okay, now I'm looking at the cubic fit. I quite like this one. I think this is probably my favorite fit out of the ones we're looking at. And you can see the Bootstrap variation, like this one's quite a way out. So it must have not sampled much in this region here when we resampled to fit that. But you're starting to see the variation in the different cubic fits. As we increase the order of the polynomial, though, what you start seeing is the variation in the fit gets a lot bigger. So I can't go to the 26-degree fit because that system would then become underdetermined. So why am I saying that? Because I'm subsampling the Bootstrap. To get the Bootstrap, some of the rows of my matrix phi are going to be identical. And you'll see that in the notes when you do it yourself. So they're not linearly independent anymore. And for that matrix phi transpose phi to be invertible, to be full rank, those rows have to be linearly independent. So I can't do the Bootstrap sample and fit the 26th order polynomial because there's effectively fewer data points in the system. But I've gone up to 16th degree and that's still worked. So what you can see is the enormous variation in the fits that is now coming. And that turns out to be fundamental to the way we think about generalization. So there's this wonderful decomposition of the quadratic error. So this expectation I'm now looking at, the expectation is assumed to be under that true distribution. So you can't, again, you can't compute this precisely, but you can estimate it with Bootstrap samples. That's the sort of thing I might, if Ferenc and Nick think it's a good idea, get you to do for the first exercise sheet to get you to go through and compute some bias and variance for some different models. But basically, because this is this nice quadratic form, you can decompose the form of this into 2 terms. One is called the bias term and the other is called the variance term. There's also this the third term, sorry, I should say, which is known as the irreducible error. So the idea here is this is true stochasticity. You might think of it as aleatoric noise, whereas these things here are to do with the quality of your model fit. So I want to sort of just explain what those terms are in terms of these plots. So there's 2 reasons we can fail to generalize well. One is that clearly this function is not linear, right? So I don't think anyone here would think that, yes, that's a linear function, right? It's doing something more complex than that. And the fact that our model fails to capture that more complex behavior is known as bias in the model, right? And that is computed in this first term. What this first term ends up telling you is that regardless of what data set you see, you're fitting it with a linear model, and the linear model is always going to sort of underfit in some sense. And this term is very high when your model fit isn't good. Now, even though it's quite a simple model, there's still some variation in the fit, and that's the second term. So the fact that for different variations of the data set, you get slightly different fits, that also turns up in this decomposition. So it's called the bias variance decomposition. And what we see is that the variance tends to go up the more complex the model. So bias goes down as we make the model more complicated, and variance goes up. Okay. Now I'm going to skip through the regularization term there just because I want to make sure we've got time for questions, but it's in the notes. One way of dealing with that is, well, there's a particular formula that we should use. So one way of dealing with this high variance is regularization, right? So the problem we've got with bias variance dilemma is that we get a more complex model. If our model's too simple, it will never predict what we want. But as we increase the complexity of the model, we tend to get variation in the quality of the fit. And the way we tend to deal with that is with the process of regularization. So regularization involves things like parameter shrinkage. So here I'm saying penalize the original loss with the L2 norm of the parameters. And that updates the Hessian in this way. That actually makes the Hessian full rank. And the Hessian becomes this key object that shows you the curvature of that Hessian. If that curvature is too flat, your model's poorly determined, and you tend to get a high variance prediction. But this introduces a diagonal, which brings some of that curvature back. So the minimum curvature you can have is now going to be alpha when you do the eigen decomposition of these things. So various approaches to regularization are doing that. But in neural networks, that's not what's going on. So something really strange is happening in neural networks according to this traditional model. So the neural network models we use, they're not linear and they're highly overparameterized, right? They're so overparameterized that we can't examine their Hessian very often for these large models at the optimum because it's just too big. There's too many parameters. We can't compute it numerically. But if we were able to, we would find very, very low curvature. It's very, very flat. So you tend to fit these models and you end up in a very, very flat space. That means that when you're at the optimum, the loss function or the error function, so I use the terms interchangeably, meaning the same thing, is insensitive to changes in parameters. And that implies the parameters are very badly determined in these neural network models. Now, this goes against everything we thought about in terms of how generalization is supposed to work, because the classical view of generalization is the following. So in the polynomial fits, this is a figure from a paper by Misha Belkin that again is cited in the notes. In the classical world, we had underfitting, which is typically due to bias. So this is the regime of the linear model. As we increase the degree of the polynomial in the models we were looking at, but whatever our form of complexity, so here it's referred to as the capacity of your model class, our risk goes down. So our error goes down to a sweet spot where, in our case, it was probably the cubic model, wasn't it? But then as we go up to the sort of 26-degree polynomial, variance dominates. So bias dominates here, variance dominates here. The bias variance dilemma is that you end up choosing between one or the other, and you end up here making a compromise, which looked like the cubic model. Double descent is a new thing that we're seeing in neural networks. And I think, well, some people claim they knew about it before, but to me, this is genuinely new and interesting about these models. So what we're seeing is these models, these neural networks are heavily overparameterized. So what I showed you with that polynomial is this model here, the one where the capacity of the model, so this is the underparameterized or overdetermined, this is the overparameterized or underdetermined, and this is the precisely well-determined model where the number of parameters and the number of data is exactly the same. And what they're showing here is this peak. And if you remember the 26th order model, you can believe that that's not going to be fitting very well. And that's the traditional view. But what's going on in the neural networks is as you increase the parameterization, you get better generalization performance. for all these models, you're interpolating, just like you saw for that 26th order polynomial, right? So your training error is 0. But what's going on is you're parameterizing more, is you're getting better generalization. And this sits totally outside that framework of generalization I've just taught you. So there's a number of different ways of thinking about why this is going on. But the core idea across all these ways is that we are not regularizing explicitly. So I would think of it as regularization in optimization, right? So it's not coming from, in the classical way of looking at regularization, adding in a term, which is allowing us to sort of look at the parameters and do shrinkage on the parameters. It's coming from the way we are choosing to optimize these models. And that's the most interesting thing to me about generalization in neural networks. I provided a few references and links to theoretical ways of looking at. The neural tangent kernel is very interesting because it applies to deep neural networks itself, but ones with very, very wide layers, which isn't normally what we tend to apply. These other works, regularization and optimization, are being applied to linear models like the ones I introduced. And what both do is they analyze the optimization of neural networks, and they look at the regularizing effect of the initializations and the algorithms itself, because that has to be why we're getting this generalization performance. But as I say, it's a generalization performance beyond what we would expect in traditional modeling. I'll stop there because it's 3 o'clock, although I'm happy to